All right, guys, welcome back to our next video. This one is on 7.6, transformations of exponential functions. So we've been learning about graphing exponential functions and how they have an asymptote and they curl upward when they increase, or they curl downward if they decrease. And so we're going to look at taking those basic graphs. And again, just like we do with straight lines, shifting those left and right or up and down, which is called a translation. So that's when you take the graph, don't change how it's shaped or curved, just change its location. Dilations, again, is going to be stretching them out taller or squashing them down shorter, both vertically and horizontally. That's dilations. And then the last one, just like before, is called reflections. And that's where you reflect it over an axis. So from left to right and right to left, or from up and down to down and up. So without further ado, we'll jump into this and we'll do a little bit of a reminder. What does the basic graph look like for an exponential function? And as you might remember, it's got a horizontal asymptote. If it's not shifted at all, the horizontal asymptote is going to be at 0. And it's going to curl up as it does here in this blue graph. Then if you add a certain amount to the graph, that's going to shift it upwards. So you can see this red one is just a perfect upward vertical shift. And even though it looks like they're getting closer together over here on the right-hand side, if you look only at the vertical change, you can see the size of that shift is the same everywhere because the red one is just literally slid upward compared to the blue one. So that's when you add something to the back of a function. So whatever function you have, just like +5 at the back or +2 at the back, it'll move it up 5 or up 2. On the other hand, if the value is negative, that's effectively just saying that you are subtracting. So you can say f of x minus some amount, and then that's going to mean that it moved downward. So if it's subtraction, it's going down. If it's addition, it's going up. And again, same thing. You can see the green one here is just a downward shift from the original. Now, if you shift left and right, you're not changing the y coordinate. You're changing the x coordinate because the x coordinate is the side to side. So just like before, at first it might seem counterintuitive because we have the opposite sign here. It's x minus h, that we have a minus sign in the equation itself. So that means that if you have, for example, x minus 3, the actual h value is the number 3, and this would mean right 3. So we don't have any numbers on these graphs, but you can envision, like, for example, this red one maybe is right 3 compared to the blue one. So if you see x minus a number, that means it's shifted right, because you have to ask yourself, what number could I plug in for x that would get me back to a 0, which is kind of like my starting point. And if you plug in a +3 here, it'll get you back to 0. So the coordinates are all +3 compared to what they were before. On the other hand, if you see a positive, that's because when you subtract a negative, say a 5, for example, if you subtract a negative, it becomes positive. So if you see a positive in there, that actually means left 5 or left some amount because it was subtracting a negative, and the negative is left 5. Another way of asking it is, what could you plug in for x that would cancel out the +5? And of course, the answer is -5. So in that case, you'd be shifting whatever your graph was to the left. So it's really important to learn the basic shape of the graph and then apply these transformations left, right, up, down. Okay, we'll jump ahead. The next thing we'll look at, just like before, is dilations. So dilations is stretching or shrinking the graph. Here, you're not sliding the whole thing up. You're taking the points and you're stretching them out based on the axis. So if a value is 0, it stays at 0. That's an important thing to recognize. Whereas in the previous one, if I just go back real quick, you can see that this got moved up. It no longer has a horizontal asymptote at 0. That horizontal asymptote was shifted up or down with the graph. Whereas here on the stretching and shrinking, the horizontal asymptote stays at 0. But all of these points get moved up. And you can see the amount they get moved up is proportional to how big they are. The bigger they were, the more they get moved up. If they're currently small, they only get moved up a little bit because you're doubling or tripling or multiplying by some factor, whatever they currently were. So the y-intercept changes, it goes up higher, and all these other points get higher. Likewise, if we're shifting with a, if we're shrinking or condensing the function, everything is going to get smaller and lower. So how do you do this? You multiply the entire function with a coefficient at the front. And if it's bigger than 1, the graph gets bigger. because you're just literally taking the graph and you multiplying it by a number. So it's going to get bigger if the number is bigger than 1. And if the number is smaller than 1, you're going to get the graph shrinking. Notice here it says absolute value is smaller than 1, because the negative sign you want to think of as separate from the stretching and shrinking. The negative is going to tell you whether it reflected or not. So just look at the size of the numerical part to decide if it stretched or shrunk. And then the negative sign you can focus on, which we'll do on the next slide. Okay, horizontal dilations are when you compress or expand side to side instead of up and down. These we're not going to spend as much time focusing on, but you'll notice that again, instead of multiplying the output or y coordinate, you're now multiplying the input or x coordinate. And just like with the left and right kind of being opposite of what it looks like, if the a value is bigger than 1, you're actually going to compress or shrink the graph outward or inward. And if the a value is smaller than 1 or between 0 and 1, then you're going to stretch the graph out. Again, the way I like to remember this is to look at the a value and say, well, what kind of x would I need to, quote, fix it? So if I say f of 1/3 x, and I ask myself, okay, well, what do I need to plug in for x to kind of get back to normal? Well, I would need to plug in a 3, right? So 1/3 times 3 kind of gets me back to normal, multiplying the inverse. So my x values are going to be 3 times bigger than they used to be to get, quote, back to normal. So this graph is stretched out 3 times bigger than it would have been. On the other hand, if I have f of 2x, the x itself is only going to be half as big as it used to be because I'm multiplying by 2. So it's only going to be half. It's going to be squeezed inward, half as big as it used to be, again, side to side in terms of the horizontal dilations. All right, and like I said, we're going to do examples and stuff later. So this is just reminding you what you learned before. And the last one, probably the easiest, stretching and shrinking. Sorry, goodness, Morgan. Reflecting across the axis. So if you change the y coordinate from positive to negative, so here we have positive y coordinate, and here we have negative y coordinate, just throw a minus sign in front of the equation. That's going to reflect it downward. If it was already below the axis, that's going to reflect it upward. And instead of throwing a minus sign on, oh, this is, hey guys, we found a mistake in the book. How cool is this? If it's the x variable that you change, not the output of the function, then it will reflect side to side, because this side is positive x on the right, and this side is negative x over here on the left. So what is the mistake the book made? I'm going to pause the video for a second, take a look. The negative sign should not be in the front here. It should be on the inside. There we go. Now the graph would be reflected. So you're plugging a negative value into the equation, not necessarily bringing it out to the front of the equation. That'll be different. So there we have our 2 possible cases for reflections. I apologize, the book made a mistake. I make mistakes, you make mistakes, we all make mistakes. There's nothing wrong with that as long as we learn from it. Try to get better every day. All right, let's do some examples where we identify what changes are occurring. So these, you don't have to do any graphing just to say what happened. So we're looking at the parent function or base graph 3 to the power of x. So if I subtract 1 at the end, that's going to be down 1. And as a reminder, it's great if you pause the video and write down some of these examples. That way you can practice them on your own. If you just listen to me tell you the answer and copy it down, you're not thinking about and engaging with it. So try to pause the video and do some of these yourself. Maybe we'll do every other one on both sides here. So we'll skip down to this one here. Here it's x minus 5 as part of the exponent. So that means it's the x value that got changed. And this is going to be right by 5. Again, it's opposite of what you see. So we see a minus 5, but that means it's to the right. Okay, let's jump over here. We're going to do 16, 20, 24, and 34. So this one, this has a different parent function. So we can just kind of assume the parent function is whatever the graph of the base was. So like this is going to be base 4. So this plus 6 means up 6. This one we're going to say is a base 1.5. So right here I have the x value that's gotten a multiplier of 4. So it's going to be a horizontal stretch or compression. And again, like I like to think about it, is the 4 times 1/4 would cancel out, right? So the X values are all going to be 1/4 what they used to be. So this is going to be a compression. So horizontal compression or horizontal shrinking, anything that's like it's squeezed inward by a factor of 4. So all the values are going to be 1/4 horizontally of whatever they used to be. Up here, we've got the exponent, which is negative x. So if you think about an xy coordinate plane, you have positive x over here, you have negative x over here. So that means we flipped across this way to go from positive x to negative x. So this is going to be a reflection. And to be more specific, it's going to reflect over the y-axis. So left and right get flipped. Our last one has a really robust, a lot of stuff going on. We got a negative sign. We got an 8. We got a +3, and we got a -4. So all of these mean something. The negative is a reflection. And it's a reflection, it's in the front of everything. So it's a reflection over the x-axis. Take your overall function, whenever you had up top, is shifted down to the bottom. The 8 is a vertical stretch. Sorry, I don't have much space to write down here. Vertical stretch by a factor of 8. This +3 is going to be left 3. It's left and right because it's attached to the x variable, which is the horizontal axis. And it's left because a -3 would cancel out the +3. And then finally, it's down 4. Because if you subtract 4 at the very, very end, everything gets shifted down 4. So hopefully these examples help cement, illustrate, and remind you of what you already learned with linear functions. And we're just now applying those same ideas to exponential functions. Okay, now we're going to look at some graphs as our final page of examples. So compared to the parent function, we're going to match each function to its graph, and the parent function is 3/2 to the power x. So it's going to be a positive exponential that's not shifted left or right or up or down or anything like that. So what we want to do is we want to snag the changes and say, okay, this one is moved up 2. So the horizontal asymptote is going to be up 2, and it's also going to be reflected. So we can look and see, hey, this one over here, sorry, it's a little behind my video, but it has a horizontal asymptote at +2, and it goes down instead of up. So this one is going to be the first one. So I'm going to label this guy A, and we'll label this guy A. The second one, we got an x +2 in parentheses, so that's going to be left 2. And it's also reflected, and it's going to be stretched out. So this is the only other one that's reflected. So we'll label it B. This one has to be B because it is reflected. Also, if we go left 2, this is our new axis right here. And you notice the graph is down 2. So normally you'd go, the intercept would be +1, but since it's reflected and stretched by a factor of 2, it's down instead of up, and it's 2 instead of 1. So from our shifted center, we go down 2 and confirm, boom, that's the second one. Number 3, this one just says -2. So that's just going to be the normal graph, just shifted down 2. So we can see right here, that's shifted down 2. So we'll call that C. No other changes. Then over here, it's multiplied by ×5. So it's going to have the same horizontal asymptote, but be 5 times bigger, which means the intercept has to be up here at 5. Remember, when you have an exponential, the intercept is normally +1 because anything to the 0 power is 1. So if you multiply that by 5, anything to the 0 power, and then times it by 5, you're going to have a value of 5. So if we call this graph D, then this would be D. All right, next one, f of 5x. So here, think about the x value would have to be 1/5 to balance it out. So we are going to be horizontally compressed. So everything is going to be squeezed inward, but it still goes through that point 0, 1, because if you compress a 0, it's still a 0. So this one has been squeezed inward a lot. And we can put down here, call that E. So by process of elimination, we know which one is F, but let's check it and see if it makes sense. Okay, this one is a shrinking by a factor of 5 vertically. So we squashed it vertically. So that intercept is no longer going to be a 1, which would have been here. It's going to be shrunk downward to a value of 1/5. So looking at that intercept on the y-axis is a really good way to kind of help figure out whether it's been stretched or shrunk and whether it's been horizontally or vertically stretched. Because sometimes a horizontal shrink and a vertical stretch look very, very similar, but keep in mind it will change where that intercept is. So that's a key thing to look at. Okay, that's it for these graphs. Again, this one was the last one. Good luck. Ask questions in class if you have any, or if you're doing this for extra credit, kudos to you and good luck with the assignment.